Welcome to this video on the science and engineering practices, or often referred to as the SEPs or the practices. Our goals for this video are to understand the intent of the 8 science and engineering practices, distinguish between these practices, and identify examples of the practices in your own curriculum and instruction. There are 2 main resources you'll want to have for this section. If you haven't downloaded these documents yet, you may want to take a few minutes to do that. You'll want to have the PDF or hard copy of the framework available while you do your alignment, and the practices reference document. I recommend you have it during this video so you can write notes on it. Now would be a great time to pause and either print or locate your copy of the reference document. Before moving on, below is an example of the KLS1-1 NGSS performance expectation we discussed in the last video. For each of these dimension videos, we'll focus on the foundation boxes. Here are the practices with language taken from the framework and expanded into the learning progression matrix. The framework authors identified 8 practices. These are often referred to with the code SEP. For the science and engineering practices, you can see both here and on the reference document. I've listed the page numbers in the framework so that you can find the relevant sections in this presentation. We will walk through one example about how you would use these documents for your alignment work. The first practice is asking questions and defining problems. The description given in the reference document is that scientists ask and refine questions that lead to descriptions and explanations of how natural and design worlds work and which can be empirically tested. Engineer questions clarify problems to determine the criteria for successful solutions and to identify constraints to solve problems about the design world. Both scientists and engineers also use questions to clarify ideas. Something that's really important for our classrooms is that we're allowing our students to have the opportunity to ask these questions. Traditional lecture style or the rhetoric of learning feeds students these recipe-style labs and lessons for them to do science. But this traditional style we know is not supported by the cognitive sciences and is an injustice to our students. There needs to be a sense of wonder, and in the same sense, everything is not known. Without that, it's hard for students to engage in meaningful learning. This practice is challenging in our alignment judgments as we look at these items. You really want to think about whether the item asks the students to pose a question or identify a problem. Many problems provide students with questions and ask students to reason about them. But for something to be aligned to this practice, it truly needs to be that the student is generating the questions or defining the problems themselves. In order to help you become more familiar with the reference document, I want to show you one example in the document with a quick walkthrough on how to use it. As I mentioned in the last slide, you really need to have the students pose their own questions when aligning to this practice. As we discuss, that is not a very common way test items are written. However, let's suppose a presented scenario to students. They are asked to explain something that they have seen in the world, some phenomena, and then asked to pose a question that could be used as the basis to design an experiment. In other words, a question that asks students to write their own testable question. If you saw an item like this, you would want to go to the page in the reference document that has the grade level description statements for this practice, as shown in this slide. Let's zoom in on the elementary statements for this practice. We're just going to look at grades K through 2. It says that students will ask questions based on observations to find more information about the natural and/or design worlds. Now let's look at grades 3 through 5. I want to point out that at the top, it indicates that 3 through 5 would build on the experiences that students have in grades K through 2, which means that students can also ask questions about the natural and/or design world. Given that hypothetical question I posed about writing a testable question based on a description of some phenomena, these statements made it clear that it would be a pretty good fit here. So I actually used the statements directly for my alignment, or I could just take these statements and say, this seems like a good fit, and go back to the framework to look at what the author said, which is why we have given you those framework pages. We're not going to walk through a sample like this for each practice, as the structure of the document remains the same for all subjects. However, hopefully this example helps you feel a little more comfortable using this matrix document. The second practice is developing and using models. The practice of both science and engineering is to use and instruct with models. as helpful tools for representing ideas and explanations. These tools include diagrams, drawings, physical replicas, mathematical representations, analogies, computer simulations, etc. Modeling tools are used to develop questions, predictions, and explanations, analyze and identify flaws in systems, and to communicate ideas. Models are also used to build and revise scientific explanations and propose engineered systems. Measurements and observations are used to revise models and designs. One of the things that we desperately need to do in the science community is to expand the types of models we use with our students. Many students' only experience they have with modeling is the idea of making a model, like a solar system or a cell model that we commonly see on ceilings in many schools. We need to do more than this. Recently, a presentation described a rule of thumb for models. That is, if you can eat it, then it isn't a model. It was meant as a joke, but it brings home the idea that we need to think further about modeling, even for test items. To identify this practice, you should be really looking for times when students either have to create a representation or they have to use a representation to find their answer. Often the presence of a diagram is an indicator that you should think about modeling. However, in some cases, the diagram is just there for context. To meet the standards of this practice, students must actually engage and reason using the model as they come to their answer. The next practice is planning and carrying out investigations. Scientists and engineers plan and carry out investigations in the field or in the laboratory, working collaboratively as well as individually. Their investigations are systematic and require clarifying what counts as data and identifying variables or parameters. Engineering investigations identify the effectiveness, efficacy, and durability of designs under different conditions. Often we think of planning and carrying out investigations. We imagine a setting very different than the large-scale test environment. But there are indeed questions that are designed to assess students' ability to plan and carry out investigations. For example, we often see questions about multiple variables being tested at the same time, or other experimental design issues. Sometimes, to better collect responses, students are given guiding steps for individual parts of an investigation to respond to. Another new phenomena in the next generation of assessments is looking at these technology-rich environments or these performance-based, scenario-based virtual platforms for students to actually engage in meaningful science explorations in testing.